Hello and welcome. Today, we're going to build a powerful geometry toolkit. Seriously, we're going to arm ourselves with 3 really elegant theorems that can turn these complex-looking puzzles into problems that are actually, well, simple and satisfying to solve. Think of them as secret keys for unlocking proportions in all kinds of shapes. So, here's our game plan. We'll kick things off with a big idea of proportions. Then we'll add 3 specific tools to our kit: the parallel line rule, the 3 parallel lines rule, and the angle bisector rule. And finally, we'll wrap up with a quick review to make sure you're ready to go. Sound good? Let's dive in. You know, the real secret to geometry isn't memorizing a million different formulas. It's about understanding relationships. And the big relationship we're focusing on today is proportionality. This really beautiful, predictable way that lines and shapes relate to each other through simple, clean ratios. Okay, our first tool is an absolute classic. It's all about what happens when you slice a line through a triangle that's parallel to one of the sides. It creates this kind of mathematical magic that makes finding unknown lengths surprisingly easy. Let's see it in action.
All right, check this out. We've got a triangle, and it's been cut by a line segment. See those little arrows? They tell us the horizontal lines are parallel. We've got 3 of the lengths, but we're missing that top left piece, segment AB. So let's call its length X. How in the world are we supposed to figure that out?
Well, the solution lies in this powerful rule, the triangle proportionality theorem. All it says is that when a parallel line cuts through a triangle like this, it divides the sides into pieces that have the exact same ratio. And that means we can set up a really simple equation to find our missing piece. The setup couldn't be easier. The ratio of the pieces on the left side, which is x over 3, has to be equal to the ratio of the corresponding pieces on the right side. And that's 12 over 4. And once you solve that simple little equation, you get your answer. X equals 9, just like that. The theorem sliced a potentially tough problem right down to size. It's clean, it's elegant, and best of all, it always works. Okay, that was great for finding a missing length, but what if we flip the puzzle around? What if you're given all the lengths, but you don't actually know if the lines are parallel? Well, it turns out we can just use our first tool in reverse. And this is the converse of the theorem we just used. You can think of it as the detective version of the rule. It says that if the ratios of those divided sides are equal, then that line must be parallel to the third side. It's our way of testing for parallelism. So let's put our detective skills to the test. On the screen, you see 2 triangles. In one of them, that middle line is perfectly parallel to the base. In the other one, it's just a little bit off. Just by looking, you probably can't be sure which is which. But you know what? The numbers don't lie. And here's the proof. For the triangle on the left, check it out. 8 divided by 5 is 1.6. And 12 divided by 7.5? Also 1.6. The ratios are identical. So the theorem tells us those lines are parallel. But now look at the one on the right. 24 over 15 is 1.6, but 18 over 10 is 1.8. The ratios are not equal. And that tiny difference is all the proof we need to say, nope, those lines are not parallel. It's that precise. All right, let's grab the next tool for our kit. We're kind of zooming out now from just a single triangle to a slightly bigger picture. What happens when you have, say, 3 or even more parallel lines that are being crossed by other lines? This rule is such a great extension of our first one. It says that if you have a set of parallel lines, any line that cuts across them, we call that a transversal, is going to be divided up in the exact same proportion as any other transversal. So the segments created on the left will be proportional to the segments on the right. Here is a perfect example. We've got 3 parallel lines and 2 transversals slicing through them. We know the lengths of 3 of the segments, but we need to find the length of that bottom right one, segment VX. Time to put tool number 2 to work. The setup here is just as intuitive as before. We create a ratio from the segments on the left transversal, that's 20 over 8, and we set that equal to the ratio of the corresponding segments on the right transversal, which is 15 over our unknown x. A little bit of cross multiplication, and there we have it. The missing segment is exactly 6. You can see how this rule is super useful, especially for problems that might not even look like they have a triangle in them at all. All right, it is time for the third and final tool in our toolkit. Now this one's a little different. It's not about parallel lines at all. It's about what happens when you slice one of a triangle's angles perfectly in half. This is the triangle angle bisector theorem.
Now, I know it sounds a little complicated, but the idea is actually really beautiful. When you bisect an angle, cut it exactly in half, the line you draw splits the opposite side. This theorem says that the two new little segments it creates are proportional to the other two sides of the original triangle. Let's make that more concrete. In this triangle, that red line is an angle bisector. We can see the two segments it created on the bottom side are 4 and 6, and we know the left side is 8. So, what's the length of that right side y?
Here's exactly how we set up the proportion. The ratio of the segments on the bottom, that's 4/6, is equal to the ratio of the other two sides. Now, you just have to match them up correctly. The segment with length 4 is adjacent to the side with length 8, and the segment with length 6 is adjacent to our mystery side y. So our proportion is 4/6 equals 8/y. We solve for y, and the answer is 12. And just like that, our third tool solved the puzzle. It's pretty amazing, right? It reveals this hidden, predictable connection between a triangle's angles and the lengths of its sides.
Wow, okay, we moved pretty fast, and we've added 3 incredibly versatile tools to our geometry toolkit. So let's just do a quick final review to make sure you know exactly when to pull out each one.
Here they are. First up, you've got the parallel line rule and its detective-like converse. That's your go-to for finding lengths or checking if lines are parallel inside a triangle. Second, the 3 parallel lines rule, perfect for any problem where you have multiple parallel lines cut by transversals. And third, the angle bisector rule. That's your specialist tool for whenever you see an angle in a triangle that's been split in half. You see, these theorems are way more than just rules to memorize. They're ways of seeing the hidden structure and harmony inside geometric figures. They turn guesswork into certainty. So the only question left is, with this brand new toolkit at your disposal, what puzzle are you going to solve next? Thanks for watching.